Imagine an object so massive and compact that its gravity becomes powerful enough to prevent even light from escaping. That is a black hole, one of the most extraordinary predictions of modern physics. According to Einstein's general theory of relativity, mass and energy curve the fabric of spacetime. Normally, this curvature allows planets to orbit stars and light to travel through the universe. But when an enormous amount of matter becomes concentrated into a very small region, spacetime can become extremely distorted. Eventually, a boundary called the event horizon can form. The event horizon isn't a solid surface. It is essentially a point of no return. Once something crosses it, escaping the black hole becomes impossible according to classical general relativity. Not because the object is being sucked in, but because the structure of spacetime itself prevents an outward escape path. And that's where things become fascinating. At the center, general relativity predicts a singularity, where the mathematical description of spacetime becomes extreme and our current equations cease to provide a complete physical picture. But scientists don't necessarily consider this the final answer. Why? Because general relativity explains gravity on large scales incredibly well, while quantum mechanics describes nature at extremely small scales. Inside the most extreme environments of a black hole, these two descriptions appear to collide. This creates one of physics' greatest challenges: finding a theory of quantum gravity that can explain both. Black holes also aren't simply cosmic vacuum cleaners. From far away, a black hole's gravitational influence depends on its mass just like other massive objects. Matter can orbit black holes, and supermassive black holes are believed to exist at the centers of many galaxies, including our own. And we have powerful evidence that black holes are real. Scientists have detected gravitational waves produced when black holes merge, observed their effects on nearby stars, and captured images showing the shadow of a black hole surrounded by glowing material. But perhaps the greatest mystery involves information. Stephen Hawking showed that quantum effects should allow black holes to emit a faint form of radiation, now called Hawking radiation. This means black holes may gradually lose energy and eventually shrink. That raises a profound question. If a black hole eventually disappears, what happens to the information about everything that entered it? This is known as the black hole information problem, and it remains an important area of theoretical physics. Black holes may therefore provide clues about the deepest relationship between gravity, quantum mechanics, spacetime, and information. Some ideas about black holes, such as using them as portals or gateways to other universes, are fascinating possibilities in theoretical speculation, but they are not established facts. So perhaps the true significance of black holes isn't simply that they are dark objects in space. They may represent one of nature's greatest laboratories, places where our current understanding of physics is pushed to its absolute limits. And that leaves us with one captivating question: what if black holes aren't where the laws of physics end, but where our journey toward a deeper understanding of the universe truly begins?